In the previous lesson, you learned about energy and conversion for different cases. Today, we move on to work, and the concept of work is closely related to energy. Before that, let's look at these two pictures here and try to guess, is there work done? The picture on the left hand side showing you a prisoner trying to move a wall, and the picture on the right hand side showing you a little boy trying to move a weight, and he's actually using his one finger to move the weights up and down. Okay, so is there work done for the left hand and the right hand side case? You can pause the video to try to think about that. And answer is, the guy on the left hand side is not doing any work, and the guy on the right hand side is doing work. Okay, so what's the difference between these two that we can categorize them as doing work and not doing work? Okay, answer is very obvious, is when the thing that you move is moving, or the thing that you try to exert a force on it and it moved by the force. Then we say if there is distant move, then there will be work done. So like I said just now, if you exert a force on something and that thing move, then we say there's work done by the force. For example, Captain Jack Sparrow trying to push the little boat into the seawater. Okay, so there's also friction that is always opposing the motion of object, and friction is a force, is a type of force, and therefore we say that if the object move against the friction, then we say there's work done against friction. There's also work done by gas. So when gas expand against the atmospheric pressure, that means the pressure of the gas inside this cylinder, for example, is larger than the atmospheric pressure outside, then it will expand or it will push the piston away. Then we say that there will be work done by gas. All right. Now let's look at the definition of work done. So in work done, there are two quantities. One is the force and one is the distance. And basically, is the product of the force and the displacement in the direction of the force. Okay, sometimes we say distance move in the direction of the force. Okay, so which means that the force and the distance, as you look at the picture on the right hand side, these two components, they should always point in the same direction. So W equals to F times S or F times D sometimes. And if we compare the base unit of F times S with energy, okay, then you should be able to work out that basically they are the same unit. Okay, so take some time and try to break down the base units of force and multiply by the unit of distance to see whether it's the same as the unit of the energy. Okay, you can use half mv square or mgh as the example for energy. Okay, so let's try to go back to the work done by gas just now. Okay, so we have W equals to F times S. All right, but for the case of a gas inside cylinder, we cannot actually measure the force. What we measure usually is the pressure. So what we can do is we can change the force into in terms of pressure and the area that the force is exerting on. So we have F change into pressure times area and the S. So area in this case basically is the cross-sectional area of the piston. Okay, so that would be something like a circular shape. That's a 3D. Alright, so this is the area here. Okay, And if it move dx, so dx here we can actually change to change in s. And the x is to represent a small distance move, so we can change to delta s. So pressure times a, and change in a small change in distance. Alright, so you see that I bracket the a and s. Basically this is the small change in the volume. Small change in the volume as it move away, okay, or as it push away and leave an additional v, delta v, to the space inside. Okay, so for pressure, work done by gas, we have W equals to pressure times change in volume. Right, go back to the force times distance just now. When we have a force and the displacement going in the parallel direction, then work done will be equal to the product of force and displacement, or distance moved. If we have the force not parallel with the distance moved, so what we can do is we need to find the component of the force that is in the same direction as the distance moved. So example, in this case here, there's a force at theta above the horizontal. So if we resolve that, that will be F cos theta times the distance moved, say S here. So then we will get work done equals to F S cos theta. Okay. We also have some odd case here. That is a waiter that is trying to lift the food with the force from his hand in a vertical direction, as shown in the picture here. So, and the distance move is d. Okay, and you can see that he said this is great pay for not doing work. Why is it not doing work? There's a force and a distance move, but he say he's not doing work. Let's try to reason that out. Just now we say that we have to use the force that is in the same direction with the distance move. Okay, so if this case, which is perpendicular, and we know that we can never resolve a vector into a component that is perpendicular, okay, which means that there's no component of force in the direction of the distance move. So basically it will be 0 because there will be no component of the force in the direction move. Okay, there are other situations like there's the sun and earth move around the sun, right? So we have earth move around the sun, and we know that earth move around the sun is because of the gravitational force from the sun, and the instantaneous movement or direction of movement basically is perpendicular to the direction of the force, and therefore this is a similar case to what I've said just now, that we can never resolve a force perpendicular to in a perpendicular direction, and therefore for rotational motion, example the sun and the earth, will not have any work done by the force.